Hello Year 11. Today we're going to do about terminal velocity, and here's the work folder. So let's go into the PowerPoint, and then afterwards we will do an exam question. So here's the PowerPoint. Right. We're doing about terminal velocity, and for grade 3 you need to know that gravity, you need to know how gravity acts on an object, and if there are no other forces acting on it, gravity will accelerate that object downwards. If you're standing on a planet. And remember, gravity pulls you down, and the force you're feeling is your weight. Now the value for acceleration due to gravity is 9.8 meters per second squared. So let me just write that on the PowerPoint. That's the pen. So the value, this is 9.8 meters per second squared, or 9.8 newtons per kilogram. These two units are the same thing, so just remember one of them. I think newtons per kilogram is the easiest one to remember, because if I 1 kilogram, if I have 1 kilogram, that has a weight of 9.8 newtons. What this is saying is the Earth gives you a weight of 9.8 newtons for every kilogram you have. So the equation, we'll get onto the equation later. Okay, here it is. Mass and weight and gravitational field strength. You need to know this equation. You also need to know that gravitational field strength of Earth is 9.8 newtons per kilogram. Okay, now let's have a look at today's lesson, which is terminal velocity. So let's go on to this slide. So let's say you're in a plane and you're a person and you get thrown out of the plane with a parachute on. Okay, you're a skydiver. So the plane goes along, throws you out. So initially you've got a weight force going downwards that's big, and air resistance going upwards that's small, because you're not falling very fast. So it looks a bit like this. So you start to fall, but your resultant force is acting downwards, so you also start to accelerate. So as long as the green force, which is your weight, is bigger than the red force, which is air resistance, you will accelerate downwards and you will get faster. Eventually, as you get faster, air resistance gets bigger. So this is the gradual process. As you start to fall faster, air resistance starts to catch up with your weight. So as you go down, the red arrow would be getting slowly bigger and bigger and bigger. And then eventually the red arrow and the green arrow are equal in size but opposite in direction. So now what you've got is your terminal velocity. Let's say you're traveling at 10 meters per second. Okay, that will be your velocity until something changes. Either you hit the floor or you pull your parachute. Because the weight force and the air resistance force are equal and opposite, you will have a constant speed forever. Now, when he jumps out the plane at the start, the forces are unbalanced. This causes him to accelerate downwards in the direction of his weight. As his speed increases, so does his air resistance, and eventually air resistance becomes balanced with his weight, and now the skydiver will fall at a constant speed. So that is this picture here. Okay, we call this terminal velocity. Now let's look at this graph. Here we have got a height time graph. Now we've seen one of these before, but we haven't called it height time. If you think about this, this is a distance time graph. Okay, so which points is the skydiver falling at a constant speed? Well, remember we said in a distance time graph that is a straight line. Now let's see, that's curved. So if this is a curved line here, this person is accelerating. Okay, and this line here is also curved. So that person is accelerating between A and B and B and C. But between C and D, is a straight line. Well, at a constant speed, what distance does this diver fall? Well, at C it's 500, at D it's 0. So this person falls 500 meters. How long does this take? Well, C starts at 30 seconds and D is at 80 seconds. So that's 50 seconds. Calculate this person's speed. Well, speed equals distance divided by time. We've already worked out the distance and the time. The distance this person fell was 500 meters. The time it took to fall, that was 50 seconds. So if you type that in your calculator, or you could just cancel it out, 50 over 5, 10 meters per second. So that is the person's speed. That is the kind of calculation you'd be asked to do. So let's just skip past this. Now, after some time, the skydiver pulls the ripcord and the parachute opens. The skydiver and the parachute are shown in the diagram below. After a while, forces X and Y are balanced. Underline the correct answer in each line below. Okay. After a while, forces X and Y are balanced. So force X has increased. Okay. Because remember, this person was falling like this before. They had that. That was what they had, like that. They were going at terminal velocity without the parachute out. Then, if they carried on falling like that, they would go splat on the floor, and it wouldn't be very nice for them. So what they did is they pulled their parachute, which will slow them down. In order to slow them down, it has to increase the air resistance force, and this is your air resistance force here, right? And this is your weight. So what happens is when you open your parachute, it gets bigger. Okay. Then what happens is over time you start to slow down, right? And as you slow down, your weight force is still exactly the same as before, but the weight force of your parachute and the air resistance or drag, I prefer to write drag because it's quicker than writing air resistance, goes back to what it was before. So initially, when you pull the parachute, force X increases, but if you look at the question here, it says after a while they are balanced. So because your weight stays the same unless you chop your leg off or lose a shoe or something, for it to go back to being at constant velocity, force X has to stay the same, and also force Y has to stay the same. Okay, but the speed of the skydiver decreases. Right? Force Y, which is your force here, always has to be the same unless you lose a foot or an arm or, I don't know, a piece of clothing. And for these forces to be equal and opposite, for them to be balanced, force X would have had to stay the same too. Right. Terminal velocity only applies to an object falling through fluids. Okay. What is a fluid? Well, that is either a liquid or a gas. It is a science way of saying a liquid or a gas. So if they ever say something about a fluid, it's not necessarily talking about water. Now, so if something's falling with terminal velocity, what that is saying is the forces of weight and drag are balanced. So there's a person, there's drag, there's weight. These are equal and opposite, so they're balanced. So the resultant force is 0. Remember, if you have a resultant force of 0, you move at a constant speed. In this case, that constant speed is your terminal velocity. So there it is. You fall at a constant speed, and we have a special name for this called terminal velocity. Now, what we're going to do is quickly do one of the exam questions. So let's do this in a bit. So this is kind of application of knowledge to an experiment. This is the classic one they like to do. what you do is you get a ball bearing, you drop it in oil, and you see how fast it falls, because it's easier to find the terminal velocity in something like oil that's more dense than air. So, a student investigated how the speed of a ball bearing changes as the ball bearing falls through a tube of oil. Figure 1 shows the equipment the student used. So you've got a ball bearing at the top here. You've got a measuring cylinder or a tube. It is filled with oil, and the marks on the tube are 10 centimeters apart, and then you've got a stopwatch. So what happened? Well, the student measured the time taken for the ball bearing to fall different distances. Each distance was measured from the top of the oil. What is likely to have been the main source of error in this investigation? Well, the main source of error is the person's got to look at the ball bearing and press a stopwatch at the correct time. So you could say that. If you wanted to go, say a general one, we call this one random error. If you said human, you don't get human error. Random error is human error. So instead of saying human error, you have to say random error. Now, specifically, I would say the chances is the person presses a stopwatch at the wrong time. So stopwatch too early or too late. Early, E-A-R-L-Y, or late. That's the biggest source of error. Now, usually, questions like this, and I can't remember the end of this question, they will ask, how would you improve this? Well, the easiest one, which is pretty much applies to every single experiment, is record it on your phone. Have this everything as it is, record it on your phone, press pause when you think it's at the right thing, and you can go back frame by frame until it is, and then you've got the exact answers. So let's have a look at B. Figure 2 shows the student's results plotted as a graph. The student identified one result as being anomalous. So remember, the word anomalous means it does not fit the pattern. Not fit pattern. The result looks like it's wrong. Look at all these lovely results along the line, then you've got this one result that's kind of like out. That's the word you've got to use. You've got to say anomalous. Now, use the correct answer from the box to complete the sentence. The anomalous result was caused by the stopwatch being started before, after, or as the bearing was released. Now let's have a look. It looks like it should have been 50, but the timer was too long. So the timer was stopped too late. So if the timer was too long, you must have started the stopwatch before the ball bearing was released. What can you conclude from the graph about the speed of the ball bearing during the first 4 seconds? Well, let's have a look. 0 seconds to 4 seconds. Now this is a distance time graph, and that line is curved. So if the line is curved, this object must be accelerating. So it's speeding up, you could say. Or you could say it's accelerating. It says about the speed, so I'm going to just say speeding up. Now the more correct word would be acceleration, but we'll keep it simple. Part 3. The graph shows that the ball bearing reached its terminal velocity. Describe how the graph would be used to calculate the terminal velocity of the ball bearing. Well, let's have a look. I would say from about here onwards, this is a straight line. Yeah, so that looks like it's about a straight line. How would you use this graph to calculate the terminal velocity? Well, we know that speed equals distance divided by time. So you could describe this. Now the answer, this question specifically is looking for the answer, calculate the gradient. But if you didn't remember that the gradient of a distance time graph is the speed, that's fine. You just remember speed equals distance divided by time and you describe what you do. So let's go back down here, the question. So if you couldn't remember that, that's fine. You can write, well, speed equals distance divided by time. So then you could plug values in, or you could say, you would just say, find the distance it traveled, find the distance it traveled, find the time, use this equation. What you've actually done there is describe how to calculate the gradient, but that doesn't really matter because you've still got the answer correct. Part 4. The directions of the two forces acting on the ball bearing as it falls through the oil are shown in figure 3. Explain in terms of the forces shown in figure 3 why the ball bearing reaches its terminal velocity. Well, here you can see weight is a lot bigger than drag to start with, but gotta remember, as this ball gets faster, the weight will stay the same, but the drag will get larger until they are equal. Okay, so what happens? Well, as ball gets faster, drag force increases. Yeah. And as the drag, eventually it will reach equilibrium. Or you could say eventually drag, oh, that's going to be a D, drag and weight forces are equal. And there you go. You can say they're equal, or you can say they're the same size. When they're equal, it goes to terminal velocity. Part C. The student repeated the investigation using warmer oil. Figure 4 shows a set of results using the warmer oil and the set of results using the cooler oil. Let's have a little look then. Well, it looks a bit to me 60 centimeters is the end of the experiment. This is the end, right? And if you look at the warmer oil compared to the cooler oil took almost 8 seconds for the ball to go to the bottom. The warmer oil took about 6 seconds for the ball to go to the bottom. So what you could say really is it was definitely faster in the warmer oil. So let's have a look. Compare the two graphs in figure 4, which we've just done. Use the correct answer from the box to complete the sentence. After falling 40 centimeters, the drag force on the ball bearing in the warmer oil is blank, the drag force on the ball bearing in the cooler oil. Explain the reason for your answer. Okay. So let's see 40 centimeters. Let's go here. There's 40 centimeters. There's 40 centimeters. Now, if I was to think about this, right? Now, I've told you before that the steepness or the gradient of this line tells you which one's going faster. So I'm going to say that this one, it's kind of, it's not going to let me do it. So I'll undo that. Right, the steepness of this graph, or the gradient of this graph, tells me the speed. So the one that is steeper is the faster one. Now, this one is kind of going this steep here, whereas this one is only going that steep, right? So you can kind of see that that line is steeper. It's a bit difficult if you don't have a ruler in front of you, but you can see that the line curves up a lot more, and you know this experiment finished first, so the ball had to be going faster. So, if this ball is going faster, then the drag force at this point must be, well, you'd think it would be larger, but remember, it's not quite at terminal velocity yet, I don't think. It's a curved line. So because it's not going at terminal velocity, it must be less than. Right? Here you've got terminal velocity, you've got drag force, weight force equal. Yep. Here, this line looks like it's still curved. So this is, even though this ball is going faster, because the warmer oil has less resistance, okay, this is still accelerating downwards, so the drag force is going to be smaller. So I'm not going to write it there because I don't have space. So explain the reason for your answer. Now this is probably the most difficult question you'd get, this one that I've just gone through here. So you need to say in the cooler oil, so let's say at 6 seconds, right? No, 4 seconds, at 4 seconds. At 4 seconds, cooler oil was at terminal velocity. Terminal velocity. So that means that weight force equals drag. Now, warmer oil was still accelerating. So it was still accelerating. Why? Because the line was curved. So therefore, I think that should get you the marks, because you've got 1 mark for this, 1 mark for that, 1 mark for that. But I'm going to keep going. I'm going to clarify this point and say, so weight WIGHT was bigger than drag. And that is the last question. So there's some very difficult questions there, but I've talked you through the reasoning for them, so hopefully that helps a little bit. So once you've done your notes and listened to this and had a go at these with me, please send them in to me via email.